Just a touch mark. Come on, there. Now, at least on my screen, I can read that line, and I can, if I push this a little bit, I can read the bottom line, but I don't know what you can see. Okay, good. So we are working on finding derivatives using shortcut method. Yesterday, we found the power rule, and we're going to do more of those. And that's what it looks like as a formula, that the derivative is a x to the n minus 1. Here are a bunch of questions that involve using that rule. And I like to use this, the English description of the rule. So you'll hear me say multiply by the power and then reduce the power by 1 a lot. And that's essentially how you differentiate, 5x cubed minus 10x, things like that. But it's also how you can differentiate square roots and 5 over x squared and all sorts of cool stuff. So it's a very powerful rule. It has a lot of mileage in it. We're going to show you a new one called the exponential rule. Not as useful yet, although this rule kind of pops in and out from time to time. Then we're going to look at what are called higher derivatives. If you find a first derivative, and then you find the derivative of this guy, it's called the second derivative. And if you find the derivative of this guy, it's called the third one, and so on forever. And then we're going to look at some questions where you have to do a bit of algebra before you can find a derivative. And then some applications, I guess, finding equations of tangent lines, for instance, or finding velocity and acceleration, and a couple of other things as well. So that's kind of where we are. I think I'll jump right in just by picking a function and using the power rule. And I'm going to start with nice, easy situation just to get the thing going. If you had to find the derivative of that function, it's basically the power rule. So you multiply by the power and reduce the power by 1. You multiply by the power and reduce it by 1. We technically never write x to the 1. We just write x. That's just a rule. If you differentiate 4x, you get 4, and if you differentiate a constant, you get 0. And that means you can differentiate really any power of x you like in a matter of seconds. So you could have a situation like that guy. Now, if you want to find its derivative, you don't get frightened by the 50. You just multiply by the power and reduce the power by 1. You multiply by the power and reduce the power by 1. Now, in this answer up here, there was nothing to do. Style points is already there. And the rule for that one is, does it look like the original? Yes, it does. Can I factor the heck out of it? Well, I guess I could pull out a common factor of 4 now I'm thinking about it. So if I pull out a common factor of 4, I get that. But that's as good as it can go. On the other hand, this guy here has got a lot more mileage in it. And so I would be pulling out 100 x to the 49 as a common factor. And that would leave me with 1 takeaway x to the 50. You comfortable with pulling out common factors? In other words, factor the heck out of it. You shouldn't really expect too much out of polynomials. There'll be a lot of situations where the answer is just the answer and you didn't need to do anything. Yeah, I'm not even sure pulling out 4 makes that any nicer looking, but technically it is what you do. Here it's a little bit more useful. And so you should do style points. And remind you what the 3 rules are. Rule number 1, make it look like the original. Rule number 2, factor the heck out of it. And rule number 3, if it's a trig expression, try and use an identity if you can and make it nice. Now let's move and show you a new guy. Let's show you this guy. We didn't even tackle that guy by the limit as h tends to 0 or x tends to a, right? We didn't do it from basics. So you're really going to have to do a kind of I believe you. Is that not an interesting result? That the derivative of 3e to the x is just 3e to the x. In its simplest form, isn't the derivative of e to the x then just e to the x? And that isn't actually a coincidence. You know, e is just a number 2.7128 roughly. It's like pi, it goes on forever. E was chosen as the base that had this property. Right? What base, right? What some number to the power of x would you need? What would the number have to be so that its derivative was the same as itself? Because having a function that has this property is very helpful in mathematics, because doesn't it make derivatives pretty, and it allows you to deal with them. So that was interesting. Suppose you had a function where it was 2 to the x. So we call 2 the base and x the exponent. The formula for the derivative of 2 to the x is over here. The base is 2, so 2 to the x. You get the natural log of 2 times 2 to the x. Now you might think, well, that guy there doesn't seem to match this rule. Well, let's show you that it does. According to this rule, right, the derivative of 2 to the x is the natural log of 2 times 2 to the x. The derivative of e to the x should be the natural log of e times e to the x. What number is the natural log of e? So isn't this just a special case of that? Functions where the base is not e are pretty rare, so don't expect to see many of those guys. But for the 1 or 2 times that it'll pop in and then disappear, you kind of need to know what its derivative is, right? So e to the x on the other hand is much more likely as a potential derivative to be asked for. Okay, let's change variable names to z. This particular one is a version of question 6. Now, this particular question has been written in a form that is good to go. Would you agree? I can use the power rule on these. I didn't need to do any algebra, which is nice. The derivative, multiply by the power and reduce the power by 1. Multiply by the power and reduce the power by 1. Now, in our list of style points, that's actually the answer. Because doesn't it look like the original? I mean, it's ugly, but the original is ugly. So don't worry about making it look anything different. Now, if we move on to something like a version of 8, let's say that guy. This involves us rewriting it as powers, right? So 1 over t becomes t to the power of negative 1. If it helps, can you think of it as 1 over t to the 1? And 1 over t to the 8 gets me t to the negative 8. Now we want to differentiate this guy. Multiply by the power and reduce the power by 1. Multiply by the power and reduce the power by 1. That's the power rule. That's the derivative. Is this guy considered simplified by the rules of style points? No. So this guy is going to have to look more like him, right? And this one's going to have to more like him. A negative power can be written as 1 over its positive. You all comfortable about the 8 staying on the top and the t to the 9 going on the bottom? And that would be you finished. Oops, it's just S dash. This is a trick question. I'm telling you right off the bat, this is a trick question. What is the derivative of the square root of 3, nice long pause, w, plus the square root of 3? See if you can get the answer without getting caught by the trick question thing.
Root 3.
Root 3.
Root 3. Isn't 5w5 and 7w7, square root of 3w is root 3. What was the problem? Do you know people, when they see the square root of 3, try and treat it the way they would do that? And so they would call it w to the half, and then they'd do that thing, and then they would do that thing, and then finally they would do that. And they would wrongly say that this answer is 1 over 2 square root of 3. Do you see they're treating the 3 as if it was like a w, a variable? Hopefully you would never do that, right? The derivative of any number, and that's just a number, is always 0. For instance, what's the derivative of e to the x plus e cubed?
E to the x.
Isn't e cubed just a number? And isn't the derivative of e cubed 0? Doesn't it seem tempting, at least, to say plus e cubed? Is there a part of you that came with thinking, I want to do that, right? But you have to hold that temptation, right? Square root of 3s are just numbers, e cubes are just numbers, right? And if I put plus 5 squared, wouldn't the answer still be e to the x? Because 5 squared is just a number, it's 25. It's not 2 times 5 to the power of 1, right? It's not, don't do a power rule when you shouldn't be doing power rules, right? They only happen when there's an x or a t or a variable. Okay, you didn't seem to fall for that one, which I'm pleased about.
Professor?
Here's the version. Yes.
Regarding question 9, I will say that on the website, it almost looked like the w was under the radical. It almost looked like the square root of 3w.
Uh-huh.
At least on my screen.
Yeah. On mine, it's a little bit less. But, well, let's show you the difference. Let's suppose that I wanted to do that guy. So you see how the w is inside the square root? Okay. Now, next to it, I'll do a big long pause, right? That version, right? Now, that version's pretty straightforward. Doesn't the derivative just square root of 3, right? This guy is not so obvious. What you would have to do here is break it apart like that. So the square root of 3w would become the square root of 3 times the square root of w. Okay, that's allowed. 2 things multiplied inside the square root. I would then change the w to a fractional power. And now I would differentiate. Multiply by the power and reduce the power by 1. Two on the bottom and that guy in the bottom. Style points now. And then I could probably make it a little bit prettier. I'm not going to try and rationalize the denominator. I could probably call it that, right? Stick them inside the single square root and then the half. So quite a different looking answer, isn't it? Depending on where that W is. Inside the square root, quite an ugly question. Outside the square root, very simple question. Okay. Now 10. That's not 10. This is 10. Oops, get the letters right. G of x, 1 over the square root, plus a cube root. We did one like this yesterday. So first thing we've got to do is to rewrite these in a format that's going to allow the power rule. Okay, so each one of these terms, it has to be rewritten as a power of x. Okay, any volunteers for 1 over the square root of x? What the heck would that look like as a power of x?
1/2.
Agreed. And what about the cube root?
2/3.
No. I think
3
that's
halves.
because you're saying,
Wait, is that 3?
yeah, it's a 3. Probably the way I've written it. There. Does that help? So cube root.
Yes.
A cube root is 1/3. Right. Now, if it was the cube root of x squared, it'd be 2/3, right? But if there's just a single radical outside, in this case, the cube root, that's what you get. Now, you want to differentiate this guy, multiply by the power, and reduce the power by 1. Multiply by the power, and reduce the power by 1. And these guys now have a bit of algebra to do. We've got to make it look like the original. So I'm going to do that guy for him, and that one for him. And x to the 3 halves is the square root of x cubed. See what 3 halves looks like, right? Square root of x cubed. And 2/3, the 3 tells me it's a cube root, and the 2 tells me it's x squared. This is the answer in its style point format. The calculus, the derivative part was only that line there. You see, most of the work was algebra, isn't it? You know, putting a thing into a format that you can do the power rule in, and then making it look pretty once you finish differentiating. It's the end of that basic type of derivative, right, where you're good to go. I want to look now at some strange ones. There's always strange ones, but here's a strange one. Question 12 looks very like this one. Now, I'll tell you what you're not allowed to do. It'd be nice if it worked, but you're not allowed to say, well, I'll just turn that into x, 9x to the half and differentiate it. If I differentiate that, I'll get 3. And if I differentiate that guy, I'll get 4x. So all I'm going to do is differentiate each piece on its own without, you know, worrying too much about what they look like. Now, it'd be great if that was the rule, wouldn't it? It'd make life very simple if all you needed to do to differentiate a fraction would be to differentiate separately all the pieces that are inside that fraction. That will never work. I mean, you'll get an answer, but it won't be correct. and you can check it out by, putting in a value and saying, it's not the tangent line. It doesn't work. Right? So when you have an expression that has a fraction in it, until we show you a rule called the quotient rule, which kind of makes it a little bit easier to do, what we have to do is rearrange this so that it's separate powers of x. So there's a number of different approaches to that. The first thing I'm going to do is just turn the square root into a half power. Okay. Any suggestions about how I could deconstruct this fraction into separate bits?
Multiply by 2x squared so you can get the denominator to the numerator.
Okay. I'm going to, most of what you said was bang on. I'm going to adjust it a little bit. That 2 is not going to come up there. What I am going to do is multiply by x to the -2. Now, forget the 2 for a minute. Isn't x squared on the bottom the same as x to the -2 on the top? See the algebra for that? Now, why is the 2 not coming here? Well, that 2, if it was going to go here, would have to be 2 to the -1. So what I would do with the 2 is I'd just stick it over here as a half. Now, if you distribute all of this stuff, you get 9 halves, x to the -3 halves, and you get 3 halves, x to -1. And that would do your job, right? You've now got it into individual powers of x, and then I could differentiate it. I want to show you a different approach to that same question. I'm going to split it like that. Okay, if you've got 2 terms on the top and 1 on the bottom, you are allowed to separate them. Would you agree that if you add these 2, you get back to the original, right? So it is allowed. And then what I would do is I'd say, okay, a half on the top, an x squared on the bottom, 1/2 take away 2 gets you -3 halves. An x to the 1 on top, an x squared on the bottom. Top power take away the bottom gets you -1. And you have 3 halves. So there is nothing wrong with this technique, taking that and making a negative power and multiplying it through. This is me, only a personal preference. I feel I'm more in control with this second method. It just feels to me that I know what's going on, because there is a very strong tendency, isn't there, to put a 2 here, in which case your fraction terms won't actually be right. You see, if you do this method, isn't there less chance that that 2 will get changed in a way it shouldn't be? But whatever method you use, you get to here. And so the derivative is going to be multiplied by the power and then reduce the power by 1, multiplied by the power and then reduce it by 1. And then we have to try, as best we can, to make it at least partially presentable. There. Later on, but not this week, we're going to show you that you can do even more of that. But right now, that's good enough. Any questions? Right. For the most part, haven't we just been using the power rule with uglier and uglier situations? Ones that you have to do more to get it to the point where you can actually do the differentiation. How about this one, which is question 13? It just popped in. to quote an old sci-fi series, although I think they made a newer version of it. You may know this quote. Danger, Will Robbins, danger. Anybody want to have a shot at the derivative of this expression?
I would think that the first term is going to be 2.1 times x to the 1.1
Correct.
plus e to the 2.1. Oh, no, I take that back because e to the 2.1 is a number, not a variable. Sorry, I haven't had enough coffee yet. So that the final answer on
you caught yourself perfectly in time, right? Can you see how tempting it is when you have a 2.1 over here that it'll influence you how you look at that? But you caught it exactly when you should have before you wrote anything down, or I wrote anything down. E to the 2.1 is just a number, isn't it? Just like e squared or the square root of e or any other e that you can think of that only has numbers. And aren't the derivative of even the weirdest ones just zero? Right, so you have nothing really to concern yourselves with. Actually, that's the answer. Can't do any more to it. I noticed 14 with a Z in it. Right, that's another one of those fraction ones over here. Right. Now this one does lend itself really well to just multiplying through by Z to -2. Would you agree that would come out really nicely? And if you did it, you would get that guy, this fella times this guy gets you that guy. Oh, that's an interesting result. What do you get if you do a Z squared and you multiply it by Z to the -2? What does that become? Z squared multiplied by Z to the -2.
1.
Yeah, you get Z to the power of 0, which is just 1. And so when you differentiate it, you multiply by the power, reduce it by 1, multiply by the power, reduce it by 1, and number 1 gets you nothing. And then you do cell points on it. And we are good. Now, you could have done that as an A over Z squared, a BZ over Z squared, and a Z squared over Z squared, right? And you would have eventually got the exact same answer. But you know, sometimes one method, for instance, that one, I think this method's a little bit more efficient. So, you know, you adapt. Sometimes one method looks better than others. So, yeah, is a puzzle. I want to differentiate that. It's not ready to get differentiated. Agreed, you got to do stuff.
Factor out.
I agree. So that guy times himself. Now, if you do the F, you get T squared. If you do the O, well, T times 1 over T gets you 1. If you do the inside, you also get 1. And if you do the last one, a 1 over T times a 1 over T would get me 1 over T squared. And so I would have T squared plus 2 plus T to the -2. And now I could differentiate. So in this case, multiplied by the power, reduce it by 1. That number gets you 0. Multiplied by the power, reduce it by 1. And then always finish with, do I have any style points? You agree? Now, if that question had been written, it's the same question, but had been written like this, I would have went through a very similar process. The only real difference, oops, wouldn't that line have been the end of the line? Look like the original. Look like the original. You see a little nuance that, you know, that's our first rule, isn't it? The style points make the answer look like the original. Answer has negative powers in it, right? Question has negatives, so should my answer. Are we good? I mean, I'm throwing as many permutations and situations as I can, and I bet you I've only covered half the combinations, whatever. They're going to be, oh, I never saw one like that before, in which case you're going to have to adapt. And this is a version of question 16. I would, well, what I would do doesn't matter right now. The only thing I would do right now is that, and I might not even write that down as its separate line of working. Okay, algebraically, how do I fix that so I can differentiate? What do I do with this fraction so that I can fix it? Because right now I can't differentiate.
Multiply by v to negative 1.
Okay, so we're doing that. Bring the guy on the bottom upstairs as a v to negative 1. Were some of you thinking of just separating it into two fractions? That would have worked equally well. So that's the two main strategies for this. So this gets you negative 2/3, and this one actually, basically the v's cancel out. And so we can now differentiate. Multiply by the power and reduce the power by 1. And that guy just gets you that guy. I mean, differentiating e to the v or whatever is so easy. I like doing that. And then I'll do style points. Am I finished with style points? Is that as good as this answer should be based on what the original looked like? No, okay. Would you agree that has to be turned into a radical? So cube root of v to the 5. We are done. Any questions? So let's move, still on derivatives, but let's move to a different situation. Let's look at higher derivatives for a minute, and then we'll go and we'll look at, because we've done a lot of these, right? Let's do higher derivatives and then some applications. So suppose I have a function. There we go. If I want to find its derivative, it's multiplied by the power and reduce the power by 1. You agreed? Now, if you use that as your starting point, you can differentiate this guy. And when you do that, use that notation, and it's called the second derivative. So multiply by the power, reduce the power by 1. Multiply by the power, that guy. Now, if you differentiate this guy, you get the third derivative. And that gets you 6. And if you differentiate this guy, you get the fourth derivative. What is the derivative of the number 6? big fat 0, right? Would you agree that if, as long as it's polynomials with positive powers of x, won't you eventually get 0 if you keep differentiating often enough? Right, it kind of slowly dissipates to nothing. Now, this is called the fourth derivative. This is called the third derivative. Now, if you wanted to do a fifth derivative or a sixth derivative, you could go into the Roman numerals. Would you agree that the Roman numerals become cumbersome after about the third or fourth derivative? Because if somebody said to you, I wanted to do this derivative, you would have to be really good at remembering what Roman numerals look like, agreed? And just let's be silly. Wouldn't you be even harder pressed to figure out what, is that the 120th? Is that the 211th? Is it 1005th? You wouldn't know. So what we do, after run about the third or fourth, we introduce this notation. It's kind of clunky, but what that means is the seventh derivative. And you see the little brackets around it? Seventh derivative. If you were doing it using, the F notation, it would be brackets around at 50. You comfortable with that notation? That it's just easier to know what the heck you're doing. Now, I can't think of many practical examples of ever wanting to find the 50th derivative.
I was just about to ask.
Except in Calc 3, where we do things called Maclaurin's and Taylor's series. And in that one very special niche market, you actually do find quite high derivatives, right? Maybe not as high as 50, but if you can't see a pattern, I guess you'd have to go as high as 50, where you have to find at least the first 5 or 6 derivatives before you can see a pattern. So that's about the only place I can imagine wanting to do it. So far, so good. So let's do a couple of those guys just to get them under our belt, and then we'll move on to some applications. So f of x is x to the 10 plus 3e to the x. And we're being asked to find that guy. Now, that means find the fifth derivative, doesn't it? Right? So, first derivative, power rule. Second derivative, power rule. Third derivative, power rule. Now we're getting to calculator world. Fourth derivative, right, multiplied by the power. Well, 7 times 720 is 5040. X to the 6. Differentiate that guy, you get 3x. And final answer, power rule. And I get 30,240 x to the 5 plus 3e to the x. Do you notice how nice it is to find multiple derivatives of e to the x's? Just a silly question, just came to my head. What would the 101th derivative of 5e to the x be?
5e to the x.
Would you agree that e to the x is a very nice function to use in any formula that you know you're going to have to differentiate things? Can you see why e is called the natural base, right? It's a natural place to go. If you want a formula, try and write them down as that. Can you remember in 141 you did population models, right? Population growth. Weren't they very often e to the power of nothing 0.123x or something? Remember those guys? Well, aren't they very easy to differentiate? Right, based on other things. The fact it's not x makes it a little bit different, but not that much. Do you feel comfortable that if I gave you a function and said I want the third or fourth derivative, that you could do it? Okay, so now we're going to get equations of tangent lines. This isn't new. We've done this before. So there's three there. Let's pick one. Version 17. And suppose I have the function y equals 9e to the x plus x, and I want to find the equation of the tangent line passing through the point 0, 9. Well, first thing you do is you differentiate. That was nice and easy. And then you find the derivative at 0, right? Because x is 0. And the derivative of 0, you'd write that notation. And that would become 9e to the 0 plus 1. Hopefully we all know that e to the 0 is 1, so that's 9 plus 1. So we get the answer 10. We're comfortable about that. And that guy, isn't that m, the slope of our tangent line will be 10. And so I have a point on the line, coordinate 0, 9. I have a slope of the line, which is 10. We call this guy x1, we call the one next to him y1. And we use what's called the point slope equation. Remember that guy? The point slope equation. That's how you get the equation of the tangent line. So y take away 9 equals 10, x take away 0. Y take away 9 is 10x. Add 9 to both sides. And we are done. So the tangent to that curve at that point, the tangent line has this equation. And I'm now going to go and check that out using Desmos. Now, if we've done it right, shouldn't it look like a tangent line just touching the curve at the point 0, 9? So let's see how that works out. Y equals 9e to the power of x plus an x. The tangent line is y equals 10x plus 9. And the point that we're interested in is 0, 9. Okay. Now I may have to shrink this and move it. There we go. The x scale is not very helpful here, so maybe I could change that. Say -1. I'll change this guy here to 1. There. Would you agree it's much easier to see? Is that, have we nailed it? Would you agree that the blue line is a tangent line at 0, 9? Everything's correct. If I'd screwed up, you know, suppose I thought that was, I don't know, -9, would you agree? Doesn't work. But it was +9, and it does work. And if you zoom in on a tangent line, it should show you this property that's kind of true. Doesn't the curve and the line pretty much look on top of each other? It's always a good sign. There's no distinguishing gap, right? Let me make that guy 9.1. Can you see the little gap now? Especially if I get closer. Whereas at a distance, it might not. Yeah, you see at that distance there, it doesn't look bad, does it? So if you really want to be sure about a tangent line, zoom in. If you see a gap, you got a problem. Now let me make that back to 9. As I zoom in on this, and just keep zooming in, you see we reach a point where everybody's the same guy, right? It wouldn't matter how much more I zoomed in, wouldn't it just look like a blue line because the blue and the red are on top of each other. And that was kind of convincing. And there are questions where not only do you find the equation of the tangent line, they give you 4 pictures and you pick the right one, right? So you pick the one that looked like the one we just did. And I'm going to have to go hunting for my page because I've lost it. I think it's here. It is. So the ones that get you to draw the thing are 18 and 19. So that's these other two. So we're now moving on to different kind of applications. The next thing we're going to be dealing with is, actually we've covered that, but I guess I should do one more. Finding first and second and third derivatives. So I guess for completeness sake, I'll just do one more. Okay. We're being asked to find the first and second derivative. So differentiate 4x, you get 4. Power rule. That guy times that guy actually isn't as bad as it looks. It's, I believe it's 9/2 x to the negative 10. And then second derivative, that gets you 0, positive 9/20, I believe, x to negative 11/10. That's not the worst question in the world, do you agree? It's just power rules. Weird fractions. 21. Here we go. We are now going to look at an application of why you might want to find the derivative. And we've seen this before. If I tell you the position function, so if I tell you the s of t, the position of an object, was t cubed take away 27t, which is a version equation 22 does, then you can find the velocity, which we'll call v of t, and you can find the acceleration at any given time, and we'll call it a of t. If you want to get the velocity, what do you do to this function to find the velocity function? You do what? Position function, what do you do to it to find the velocity?
First derivative.
Just first derivative, so you differentiate. That means I now know for this object in 2D space exactly what its velocity is at any given time. Now, if you differentiate the velocity, you now have the acceleration. I mean, isn't that kind of cool? If all I know is where something is at any given point in time, using calculus, don't I now know its velocity and its acceleration? So can you imagine Newton thinking that, you know, you can actually do this because most of the planets, we'll argue about Pluto being a planet, lie on the same plane. Isn't it like two-dimensional space where the sun is a focal point? And so he knew where the planets would be right through the observations at any given point in the year. Let's say it was the Earth, so it'd be a year. And once you did that, couldn't he then just differentiate it and he'd be able to tell you the velocity of the Earth, how fast it's traveling through space, and what its acceleration was, and all sorts of other cool stuff that nobody else could do. Now, if they asked you, say in question B, what's the velocity at the 2-second mark, or maybe what's the acceleration at the 3-second mark, you just evaluate this function at 2, and that's negative 15, and let's assume that the units were meters per second. So that's negative 15, and the acceleration at 3 is 6 times 3, which would be 18. And if you happen to be into physics, you'll know the acceleration has units like meters per second squared. So I can tell you at this point in time, isn't the velocity negative, and at this point in time, isn't the acceleration positive. I can even do things like this. Here is the velocity guy again. And I want to know, when is this object stationary? So when is this object not even moving? So imagine it was a rock being thrown up into the air, right? Wouldn't there be a point where it would instantaneously look like it was not moving, right? You know, like the basketball jumpers up in the air. Like there's that snapshot of time where they're actually not moving up or down, right? They're hanging there. We should be able to find it from here. When that happened. Well, when you're not moving, right? When you're stationary, the velocity is 0. Agreed? And we would then work on solving this equation. You could solve it a number of ways. I'm just going to do it this way. I'm going to pull out 3 as a common factor. And then I'm going to recognize that this is a difference of 2 squares. And this one gives me a solution of -3. And this one gives me a solution of 3. And I'm going to pretend that you can't do time travel. So we're going to look at 3 seconds. So at the 3-second mark, this object would actually be stationary. And you can even find, when is this object going at 40 meters per second? Can you just make this equal 40 and solve? So you can answer pretty much any object, any particular thing that you're interested in, simply by just differentiating once to get the velocity and differentiating this guy once to get the acceleration. Any questions about that? You feel comfortable? Velocity is the first derivative, acceleration is the second. I guess I should put that over here. Velocity is the first derivative, acceleration is the second derivative. So let's show you another application. Anybody recognize what curve that is? Ax squared plus bx plus c. What's that the general equation for?
Parabola.
Right. Now, just for argument's sake, can we pretend it's this parabola here, right? This is a bit of a harder question because it's kind of springing on you. Does anybody know the formula for the x coordinate of the vertex, which is that guy there?
-b/2a.
Correct. Do you remember that now that you've heard it? That the x coordinate of the vertex of a quadratic parabola is -b/2a. Let's use calculus. Right, so I'm going to start with every quadratic in the world can be written like that because A, B, and C are constants, right? They're just numbers like 42, right? Treat them like 42, right? Like just numbers. Would you agree at the vertex that the tangent line is 0? So if I differentiate this, I multiply by the power and reduce the power by 1. What's the derivative of bx?
B.
B. And be careful here. What is the derivative of plus c?
Nothing.
0.
Nothing, right? Gone. Now, if the derivative is 0, then all we need to do is find out for what value of x is this equal to 0. So how about subtracting b from both sides and then dividing both sides by 2a?
Gee, haven't seen that one before.
Is it cool?
Yeah, actually it is.
Yeah. So do you see that you can simplify a problem that was much more difficult to do in 141 if they even tried to prove it to you, right? Didn't we just normally just say, hey guys, here's something that you may want to know. If you want to know the x coordinate, here is the equation, you know. Can't prove it to you, just trust me, I'm a mathematician. Do you see that we can now prove it? In fact, couldn't you prove it for any shape you wanted, right? I could do a general cubic and figure out where, you know, these places are. For a cubic, typically, then wouldn't there be two of them? There'd be one here and one there, right? But you know, we could do it. And just a use. Where shall I go next? Yeah, suppose we give you a formula. I'm just making this up, and P is equal to 0.02a squared plus 4a, right? Plus 1.213. Now, if you wanted to differentiate this, you could call it P dashed. You can also call it dP by dA. They don't use that notation much, but they do in question 24, which this one is like. So that means the derivative, so does this. So here the numbers are ugly, but it is simply just power row, and that's a number, so you get nothing. So there's your answer. Now, if you wanted to know what this derivative was equal to when, say, a is 10, the notation's a little bit clunky when it looks like this. That means find the derivative when a is 10. So in this case, it would be 0.04 times 10, add 4, which I believe is 4.4. Are you comfortable that that's another notation for find the derivative? And this is another notation for find the derivative at a given value of a. Isn't it much nicer to use that notation? Because couldn't you just do that and everybody knows that, you know, that's the same as this. So I think that notation is just more elegant. So you might think, why do we even have this notation if it's kind of clunky? It is useful in when you actually go in and do integration. Looking at derivatives in this format is very useful for some techniques that we use, like substitution method. So it is, and it's actually now I think about it, it's quite useful in differential equations. If you ever go in and do differential equations, which you might guess by its name are equations that involve derivatives that you're trying to solve. So this notation does have a use. Are we good so far? Right, and Gordon Hammer. So, well, everyone, let's tell you the last question, and we're going to finish off today a little bit early. I have a delivery that I kind of need to be here for. So, suppose I gave you a cubic equation, and I said, find the values of x, right, the x coordinates, right, where there's a horizontal tangent line. Well, you find the derivative, which is that guy, agreed? Parallel. Now, if you're going to have a horizontal tangent line, and imagine a cubic, you can see there's two of them, right, typically. What do you know about the value of the derivative at the places where there's a horizontal tangent line? So what's the derivative going to be equal to at these two key places?
0.
Zero. So what you need to do then is solve a quadratic equation by whichever means you like. And I'm going to make this up But can we pretend that one of the answers was x equals 2 and the other one was, say, x equals 7, just for argument's sake? Then in WebAssign, they say the smaller x value, and then they have the larger x value. And the smaller x value was 2, right? And the larger x value was 7. And then you're meant to calculate the y coordinate in each case. So your answer will be 2, 101 and 7, whatever it is, 73. So last name, bye-bye. And I have to nip off and tell somebody where to put stuff. So hopefully
So
that's-
Professor, did
Yes.
you put the x value into the y or the y prime?
put that into the y's,
Oh, okay.
that guy there. If you put it into the y prime, you'll get 0. This is actually the coordinates of this point. So can you pretend that guy there is 2, 101? Right. So that's why it's the y value you put it into. Are we good, guys? Right. Bye-bye for now. You can always ask me tomorrow if there's any hiccups. And I have to leave.